This video is going to cover the variation method and how we can use it to solve for the energies of many electron atoms. In principle, this problem is going to be very similar to the one I'm going to go over in this video, but much more mathematically cumbersome. It's the same math, but there just involves a lot more variables. So the example we'll use is going to be the particle in a box. So the way that we're going to go about calculating energy is the same way we always go about calculating energy for quantum mechanical systems. So our average value for energy, our expectation value, is always going to be equal to the integral of the complex conjugate of our wave function multiplied by our wave function after it's been operated on by the Hamiltonian, the total energy operator. And in this case, when using the variation method, we're not going to be dealing with normalized wave functions. So we have this denominator. If our wave functions are normalized, we don't need to include the denominator because it's always already included in the normalized wave function. So this is true if we know the exact wave function. If we don't know the exact wave function, we're going to use the variation theorem on an estimate wave function. So the estimate wave function is going to be our energy for that, and that's going to differ from the actual true energy that's E naught there. So our estimate energy is going to be equal to the same thing, although we're going to be using our trial wave function. So phi here is our wave function that we are using to approximate the true wave function. So we don't know what the wave function is, but we're going to guess phi might be close to the wave function. So it's the same thing. We take phi, we operate on with the Hamiltonian, and then multiply that by the complex conjugate and integrate that, and then we normalize as well as phi is not already normalized. And according to the variation theorem, this is always going to be greater than our actual energy E naught, and it would be equal to in the case where we choose the actual wave function. So how do we go about doing this? So in principle, the computers that try to solve these programs are going to attempt to maximize these trial wave functions with respect to a lot of variables using an iterative approach. That's not something that we can really do on paper to demonstrate how this works. So we're just going to have one variable to be maximized. So we're going to attempt to use this variation method to solve for the energy of the particle in a box. So for the particle in the box, remember that our Hamiltonian is simply equal to negative h bar squared over 2m times the second derivative of our wave function with respect to x, and there is no potential energy for the particle in a box. And the energy values as a function of n are equal to h squared n squared over 8ma squared, or 0.125 h squared over 8, or oops, that's over ma squared for our first level of n equals 1. So we can attempt to solve this with a trial wave function, and what we should see is that our value is greater than 0.125 h squared over ma squared. So what's a good trial wave function to use? It has to it has to match the parameters of our problem. So for the particle in the box, that has to equal 0 at these boundary conditions of 0 and a. So what we can do is use a function that does that. So our trial wave function could be some series of polynomials like this. So we have x over a minus x cubed over a cubed, and then plus alpha x to the fifth over a to the fifth. And this is an example of a trial wave function that we might try. And we can take this wave function and we can evaluate it and solve for what we would expect to get. And so we'll do that by just taking this wave function here and plugging it into this expression up here. Now, this is very straightforward. So it just involves some algebra and then some simple integrals of polynomial expressions. But there's a lot going on, and I'm going to skip over a lot of that math. It's something that you could do if you wanted to, and you have to be really careful to keep track of all your positives and negatives and make sure you're doing all your integrals right. There's a lot of bookkeeping involved, but the actual math behind it isn't very challenging. And we also do if we do this for the numerator and then for the denominator. And for this particular example, what we would get at the end of the day is we would get that our energy is equal to negative h bar squared over 2ma squared, and then times this expression here. So we'll have 4/5 plus 2 alpha over 7 plus 20 alpha squared over 9. And then we divide this by 8 over 105 plus 4 alpha over 63 plus alpha squared over 11. So if you're interested, again, this is just taking derivatives and integrals, and it's very simple algebra and calculus to come up to this point, but it takes a lot of steps and being careful with your math. So once we get here, what do we want to do? Well, we're trying to find the minimum value. So we want to minimize our E with respect to alpha. So we're going to take the derivative of our energy with respect to alpha and set that equal to 0 and figure out where that is. So we could actually do that, but that's going to be a pain in the butt. A much easier way is going to be to plot this using something like Desmos. So I have that here. All right, so let's share that on the Zoom. So here we can see a plot of this function, and we can go into the function and find our minima. So where our derivative is equal to 0 is at this minimum here and this maximum here. So it turns out that this minimum is going to be equal to our minimum value. So we take that alpha being 0.139, and that is going to be our value for alpha that corresponds to the energy minimum that we're looking for. And that comes with this value of 10.172. So when we plug alpha in, our energy is going to be equal to 10.172. And you might say that's really nowhere close to where we should expect it to be. And that's because we're not quite in the right units yet. So let's go back to the iPad. And what you can see is we're looking for not h bar over 2ma squared, but we're looking for h bar over ma squared. So we convert this, so we'll get our 10.172 divided by 8 pi squared times h squared over ma squared. And when you do that, when you divide 10.172 by 8 pi squared, you get 0.129 h squared over ma squared. So we can see that our function, our trial wave function, wasn't as good. It wasn't the sine function that we know the answer should be, but it was close, and our energy that we get out is pretty close compared to the actual energy. So in quantum mechanical calculations, this is what the computers are doing. They're evaluating these expressions, but they have a lot more variables. They can tune them, and they go through these iterative approaches to attempt to calculate the energy levels. But at the core level, this is what the computers are doing when they're attempting to solve a quantum mechanical calculation.